In this video, I am going to present what I consider to be very compelling proof for the flat Earth. I have total confidence in the data collected and the interpretation of the data, and yet I still don't really understand how this evidence could be so clearly supporting the conclusion that the Earth is flat. Because how could the Earth be flat? I can't even begin to wrap my head around that concept. But the evidence clearly supports this conclusion. I stumbled onto the flat Earth about 6 months ago, and I would say that since that time I've watched close to 200 flat Earth videos, maybe 1 or 2 per day, with a focus on videos that presented empirical evidence. And out of everything that I saw over the last 6 months, I never encountered anything that conclusively proved the flat Earth to me. I ran across a lot of videos that were very convincing, but nothing that ever sealed the deal and just convinced me 100% that this was true. There was always some little shred of doubt in each video, some aspect of the evidence that was ambiguous or subjective and could be called into question. So I started trying to develop some ideas for experiments or observations I could make to prove one way or the other conclusively whether the Earth was a globe or flat. I didn't really have an opinion on the subject, but I felt that the debate was interesting. I went through a lot of concepts and actually went out and did some experiments and didn't really find anything that I thought was going to deliver proof until I happened upon this test, which is actually quite a simple idea, but I believe delivers conclusive proof of the shape of the Earth. Part of the research for this test, once I came up with the idea, was that I had to find specific geologic features in a particular alignment with one another, and that took quite a bit of time. I spent a lot of time looking at maps on the internet and ordering maps off of Amazon and eBay and looking at those, just doing a lot of different types of research trying to find what I was looking for. As it turned out, what I was looking for happened to be in a place my wife and I hike in quite often, actually. It's a really amazing place to hike. We love going up there. It's called the Shining Rock Wilderness. It's located about an hour south of Asheville, North Carolina, on the Blue Ridge Parkway. And it's a really unique place. It's unique in that it has multiple peaks over 6,000 feet that are grassy balds, whereas most of the mountains in the southern United States are covered with trees. So you can hike up there and hike over these balds, and on a day with good visibility, you have a 360-degree view of about 60 to 70 miles in which you can see hundreds of mountain peaks. So once I had identified the appropriate geologic features and mapped out the approximate locations where I could conduct the observation, then my wife and I went up to the Shining Rock Wilderness, and it took us about 6 times altogether of doing much longer hikes than we normally do. We usually hike maybe an hour and a half or 2 hours a couple of times a week, and this required 5 and 6 hour hikes to get near the areas I had pinpointed on the map. So the way the process worked is we'd get into that general area, we would be on a trail, and we would kind of set up a mini base camp where my wife would wait for me, and I would descend off of the trail and make my way through the really dense brush of the mountainsides, trying to locate the precise point where I could complete the observation. We repeated this process until we finally found the right location to conduct the test. And we ran into a variety of issues while doing this. Sometimes the ridge I was on would descend too quickly and there would be a ridge in front of me that would be blocking my view, or the ridge wouldn't drop fast enough and my angle would be wrong and I wouldn't have the line of sight that I required. It was tough to get at the right elevation and also have a view of what I was trying to see. Then we also faced weather conditions. We'd have clouds move in, or it would get hazy towards the afternoon, and I would lose that 45 miles of visibility that I required to do the test. But eventually we did find the location to do the test, and what I saw when I got there was shocking to me. I mean, before I even set up the camera or anything, and I just looked out across towards the features I had identified on the map and saw them, as I expected I would, what they were showing me was that the curvature that should have been there, it just was not there. There was no way around it. The evidence I collected proves that the Earth is flat, which is ridiculous. But I welcome anyone to challenge this evidence and show me how it says anything other than the Earth is flat. Okay, so as to the design of the test, I'd like you to take a look at this beach ball, which is obviously spherical, as the Earth is claimed to be. So we're going to zoom in on a section of the beach ball, and imagine you have three objects affixed to the surface that are all the same height and in a row. So in this case I use toothpaste caps because we're all familiar with those. The regular line that connects the tops of those caps will also connect the bases and give you a very accurate representation of the shape of the object they're attached to, which in this case is the beach ball. So get rid of the line and the caps, and we're gonna zoom back out and get rid of the beach ball. In its place, we have the globe. Again, we're going to zoom in on a section of the globe, and same thing. Imagine you have three objects that are the same height, all in a row. In this case, I chose mountains because most mountains all over the world, the elevation has been recorded, and there's lots of sources for that. It's fairly easy to find three mountains in a row that are the same elevation. It took me some time, I think this, because it was the first time I ever did it. Trying to locate this was actually pretty difficult and time consuming, because you need three mountains of equal elevation, or actually you need two. One on either end can be higher, and you can actually just go down a little lower from the peak to make the elevation. But it requires certain characteristics. Those three mountains have to be in a straight line. Two of them have to be the same elevation. The third one has to be the same or a little bit higher. And the peaks also that you're observing have to be prominent. In other words, they have to raise up above the surrounding landscape. So mountains around those mountains. And they have to be prominent enough to where there aren't any mountains in between them that are taller. So they have to be tall mountains in a row without tall mountains in between them. So it's a little challenging to find this. It does take some research and maybe even going out and doing some observations and scouting around on trails, which is what I did. But it is doable. I think if someone wanted to repeat this at this point with my help and some tips, it could be done fairly easily. And I would say that there are hundreds of instances of mountains of similar or the same elevation in a row all over the world. That being said, this is the same as the toothpaste caps. The regular line that connects the tops of those mountains will also connect the bases of those mountains and give you a very accurate representation of the shape of the object they are protruding from, which in this case is the Earth. Okay, get rid of the line and the mountains, and we're gonna zoom back out. Now we're gonna look at, instead of a sphere, we're gonna look at a flat surface. So in this case, it's a ruler. And again, imagine you have three objects that are all the same height attached to the surface. And again, we have the toothpaste caps, and again, the regular line that connects the tops of those caps also connects the bases of those caps and gives you a very accurate representation of the object they are attached to, which in this case is the ruler. And if we get rid of the caps and the ruler, instead we have a flat Earth, and 3 mountains that are all the same height, then we have the same phenomenon, that the line that connects the tops of the mountains also connects the bases of the mountains and gives us a very accurate representation of the object they're protruding from, which in this case is the Earth. Okay, so we're going to get rid of the line and the mountains and the flat Earth, and we're going to go back to the globe for a moment here, and if we zoom in once again on our section of the globe and we put our 3 mountains back, and for the sake of this demonstration we'll call this mountain number 1, and we'll call this mountain number 2, and we'll call this mountain number 3. So if you're standing on mountain number 1 and it's 5,400 feet and you're on a globe, and mountain number 2 is 5,400 feet, and mountain number 3 is 5,400 feet, then if you're looking from mountain number 1 to mountain number 2, your line of sight is straight. But the surface that the mountains are protruding from, which is the surface of the Earth, is curved. So your line of sight is straight, but the surface of the Earth is curved, and so therefore you would never see mountain number 3, because the curvature introduces declination, visible declination of mountain 3, and it's going to drop down. Particularly if this distance right here between mountain number 2 and mountain number 3 is vast, 30, 40, 50 miles, then you're looking at many hundreds and even thousands of feet of declination, which is visible sinkage of the mountain. So it's literally sinking out of view from your horizontal line of sight over the top of the 2 mountains. Okay, that makes sense. So we're going to get rid of the line of sight and the mountains, and we're going to zoom out again and get rid of the globe, and let's go back to our flat Earth and our 3 mountains on the flat Earth. So if we call this mountain number 1, and this is mountain number 2, and this is mountain number 3, if you're standing on mountain number 1 and looking across to mountain number 2, then mountain number 3 should be either just barely visible or just barely obscured behind mountain number 2. And if you're somehow able to move perpendicular to the line created by the alignment of the 3 mountains, say 100 or 200 feet, and then look across to mountain number 2, and these peaks are all prominent, in other words, they're standing individually with nothing obscuring the side of them, then if you can move 100 or 200 feet off to one side, when you look across past mountain number 2, you would see mountain number 3. And of course that's on a flat Earth. So your line of sight would be right at mountain number 3. So that's the basic premise of the test. Find 3 mountains in a row, 2 of them of similar or identical height. One of them can be slightly higher, but put myself at the same exact elevation of the other 2 and look across and record the observation and see, is mountain number 3 visible, or is mountain number 3 not visible because the Earth is curved and it has visually declined by a significant distance? That's the test. Part of my quest in trying to put this test together was not only to find 3 mountains that were the same elevation in a row, but also 3 mountains that were well known and well photographed, so that anyone watching this video could validate for themselves that indeed I was actually recording the mountains that I claimed I was recording. So one of the mountains is Tennant Mountain, which isn't actually in the video, but is where the camera was placed to capture the shot. And actually I was on a ridge down in front of Tennant Mountain. And the foreground mountains, and in particular Frying Pan Mountain, is a really recognizable mountain. It's got a Forest Service tower on top of it and 2 communications antennas.